Now we get to part 2 of the waves section of the course, where we'll be considering optics and light. What is light? Is it a wave? Is it a particle? How do we understand how it interacts with matter? Well, as we shall see in this part of the course, it can be thought of as both, and depending on what properties of the light we are wishing to investigate, we might use the wave model or the particle model. So we already know that light can be described as a transverse wave, a bit of a special transverse wave, as unlike other waves, it doesn't require a medium to travel through, but of course it can travel through some mediums like glass or water. You also probably know that light tends to travel in straight lines, and we can use this to understand images and reflections, mirrors and lenses, and this is often summarized as the ray model of light. There's lots of questions we can ask in this section of the course. How does light interact with matter? Broadly speaking, light has 4 ways it can interact with matter, depending on if there's a medium change or not. It can be scattered or absorbed, reflected or refracted, as we will see. Finally, we'll ask, how do we see and what is vision? So light is indeed a wave. We know this because the light spreads out as it travels. It diffracts, and it also forms interference patterns. We've seen interference patterns in terms of standing waves. We also observed the Doppler effect in light. Now, we didn't do the Doppler effect in sound, but you might be familiar with the sound a fire engine makes as it goes past, with a change in frequency. We also see the similar thing in light, strongly suggesting that we can think of light as a wave in this context. Light is a transverse wave made up of a coupled electric field and magnetic field. These two fields are self-supporting and oscillate perpendicular to each other and to the direction of travel. So they don't require a medium to keep themselves going. The speed of light in a vacuum is often written as c instead of v, and it's 3 by 10 to the 8 meters per second. It can travel in other mediums like water and glass. We know it clearly can go through a window, and as it goes through mediums, it undergoes a change in velocity. Light, like all waves, transports energy. What we call light is really visible light, which is really just a small part of the electromagnetic spectrum. Here is a diagram of the electromagnetic spectrum displayed as a function of frequency. Down one end we have radio waves, and up the other end we have X-rays. And somewhere in the middle there is a small slice where we have visible light. Light can be described using the relation velocity, frequency, and wavelength. So we have v equals f lambda, where v is often c, the speed of light. Light is often described by its frequency or wavelength and its intensity. The colour of light is really its frequency or wavelength, and the brightness of the light is its intensity. Humans see a small range of frequencies, these ones here, the so-called visible spectrum, where some animals like butterflies and bees see a higher or lower range, see the closer to ultraviolet light or infrared light. But it is also a particle. Einstein, pictured here, showed this in 1905, and the particle is given the name a photon. So when light is absorbed or emitted, it is done so in integer numbers of photons, i.e. it's an indivisible bit of light. The energy of a photon is related to its frequency. So light has what's called this wave-particle duality. Sometimes it's best to describe light as a wave, and sometimes it's best to describe it as a particle. That doesn't mean that sometimes it's a particle and sometimes it's a wave. It just means that sometimes we can use the wave model to describe what's happening with light, and sometimes it's best to use the particle model.